And this allows me to, this was sheer luck, by the way. This allows me to quickly introduce Natalie, who actually doesn't really need an introduction. So I've been following her research for a very long time, and I'm really impressed by all of the stuff that she has been doing. So she's a security researcher at Google Project Zero, focusing on, I think, a lot of it. I got to know her through her Tamagotchi hackery, but she also focuses on browser security, scripting engines, WebAssembly, WebRTC. Today she'll talk about adventures in video conferencing, but also she has a background in mobile security, messaging apps, and so on. I think overall she's just doing a lot of amazing research, which would be way too long for me to actually go into too much detail. And I don't really want to take away too much from her, so I would like to pass the word over to her and let her present her her talk. So thank you, Natalie, for accepting. I'm really looking forward to your talk.
Great, thanks so much. Thanks so much for inviting me.
This is working, amazing.
Yes. Yeah, so today I'm going to give a talk entitled Adventures in Video Conferencing. I'm Natalie Silvanovich, and I'm a member of a team called Project Zero at Google. Project Zero's mission is to make zero day hard. We want to make it more difficult for attackers to use 0 days against anyone they target. And to achieve this goal, we do a few different types of work. Most of our work consists of finding and reporting vulnerabilities so they can be fixed. So my average day is putting my nose into code and trying to find the types of bugs that I think attackers will use so that they aren't available anymore. We also spend some of our time writing exploits. Our goal is to understand how the exploits work so that we can think of ways to make it more difficult for attackers to use them. We also spend some of our time driving structural improvements related to our work. So this will often be things like mitigations to make exploitation more difficult, or helping vendors think of new ways to fuzz their software. So I'm going to talk today about the work I've done on video conferencing. I've been doing this for on and off for 2 years. I want to talk a bit about, how this process worked, and more specifically, how attackers behaved in the meantime and how it informed this research. When I started, I realized that video conferencing became a big thing really, really quickly. Of course, with COVID, we're using it more and more. But even before then, video conferencing software was in browsers. It slowly came to every messaging client, to WhatsApp, to Signal, to Facebook, to many others. And at this time, there was very little information available on implementation vulnerabilities. When video conferencing protocols were designed, a lot of work was done on encryption. So things like, how do you prevent an eavesdropper from seeing or modifying the stream? But there's way less on what if there's a buffer overflow in one of the protocol parsers. And I found this especially concerning because there are some people out there who use exploits for bad purposes. And there's actually exploit brokers who will buy and sell these exploits. And most of them are private, but there's one called Zerodium that actually posts their price list. To give some examples, their most valuable thing right now is Android full privilege escalation 0 clicks. So basically, if you can remotely jailbreak an Android without touching it, allowing an attacker access to everything, this company will pay you $2.5 million. Meanwhile, if you can do that in iOS, you can get $2 million, and prices go down after that, but you can see that there's a lot of different targets here. And something that I noticed was a great deal of these top value exploits involve video conferencing. So obviously, Android has a Duo installed on most devices, iOS has Facetime, And then things like WhatsApp, Telegram, Signal, Facebook Messenger, they all have video conferencing. So this seems like this could potentially be an interesting target to find the sort of bugs that attackers really value. So I looked into it, and I found that the vast majority of video conferencing is implemented using WebRTC. And WebRTC is an audio and video conferencing library that's maintained by Google, and it's used by basically most video conferencing. It's in browsers. So for example, this hop-in thing we're using for this workshop, this will be using WebRTC in your browser. Messaging applications also use it. Facebook Messenger, Signal, Snapchat, Slack, etc. They also embed this library to use it for video conferencing. I have WhatsApp in there, but they're basically the one exception. They do use parts of WebRTC, but they also use mostly an alternative called PJSIP. And the other alternative implementation is Facetime. On iOS devices, they implement their own video conferencing. But other than that, most systems don't. Most of them use this WebRTC. And at the time, basically, there wasn't any security information available about it. So just to step back a bit, how does WebRTC and video conferencing systems in general work? Well, it's a two-phase process. So to start off, you do what's called signaling. And signaling is where two peers that can talk to each other in some way set up their video conferencing call using the messages they can already send. So for example, if you're using a browser like we are now, the browser clients can communicate with the server. So the browser will send this signaling data to the server, and then that'll be exchanged with the peer, which in this case would be another server. And then that'll be the information that the two peers need to set up a peer-to-peer connection and send media. So if it's a messaging client, for example, something like Facebook Messenger, they'll use what's available to them, for example, a Facebook message, but it's always the same deal. There's this signaling information that they exchange through the secure channel, and then this is used to set up a peer-to-peer channel between the two or more devices that need to communicate. There's a lot of protocols that are used for this. On the left-hand side of this diagram is what's typically used for signaling, which is usually TLS over TCP, though, as I said, it can be anything. But on the right is how the peer-to-peer protocol usually works. And this is typically over UDP, though it doesn't have to be. There's nothing transport-specific about WebRTC, so it can use TCP or other things. Then there's ICE done in turn, and these are the protocols that are used to help peers find each other on the network. So if you're behind a NAT or something, ICE done in turn will make the two peers have readable IPs to each other. Then there's two protocols that are actually used by WebRTC to exchange peer-to-peer data. RTP, which is called SRTP if it's encrypted, I'll talk about a lot, and that is the protocol that's used for audio and video. And this is a best effort protocol. So something you want in video conferencing typically is that it's okay if you lose packets. You know, if you lose one video frame, that's okay. You know, it just makes your video go slower. But then there's also Sctp, and that's used for reliable data transfer. And that's typically used for sending small amounts of text data. For example, if you post a question in the question box here, that'll usually use data channels. And the reason you need that reliable transport is, unlike video, you need 100% of that. You don't want like one bit of your question to be missing, because that would make it not understandable. So I looked at this, and the first thing I did was I fuzzed the RTP processing. That seemed like a really complex protocol, so I thought I would start off by giving that a shot. So I started off with what I'd kind of call the worst fuzzer ever. I altered Chrome so that it now sent out malformed RTP. So I literally altered the code where the RTP was generated. And then I pointed it at a normal browser. I set up a call with WebRTC. And this crashed every 30 seconds, which was not what I expected, but it showed that this code was like really, really bad. So I learned here that the concept would generally work, and I got a few very shallow bugs that blocked fuzzing fixed. And just in case people are curious, this is the fuzzer I used. So it literally was that I would overwrite one byte with something random, or sometimes I would overwrite a block, or sometimes I would shorten the packet. So this is a very, very simple fuzzer to find this number of bugs. But then I decided that this was not enough, and I wanted to find more bugs. So eventually I wrote a client fuzzer using WebRTC in C++, which was nice. It was lighter weight than the browser. I could run it against every target. And I think like the only good part about this was that there were no false positives. Every crash I got in the browser was a real crash, but it was very slow. And it did help me find some more end-to-end vulnerabilities of WebRTC. And then what happened was that the WebRTC team got sick of me. I kept reporting all these bugs where I would be like, hey, you know, change this code, build the browser, point it at another browser. And those are really hard to reproduce. So they gave me this command line tool that would emulate RTP. So I could put the packets in a file and then use this to emulate it. And what was nice about it is this was fast. I could build it with coverage and do distributed fuzzing. What was not great about it is it was not a perfect representation. And I did some work to make it a better representation, but still, I spent a lot of time going through false positives. But what was good about this is then I could do fuzzing with coverage, and I found many bugs. So these were like the first 7 serious vulnerabilities I found, and there were quite a few that were not serious as well. And considering the nature of this attack surface and the number of things it was in, you know, I thought it was concerning. So I'm going to give you an example of one of the bugs I found. And what I like about this one is, like, I've never seen a bug like this. So I want to give everyone a minute. Take a look at this code and see if you can find the bug in it and put it in the chat. And I want to see if anyone can figure out what it is. Okay, wow. So I just got the right answer. And this says, I've done this at many presentations. I have literally never had a single person give the right answer. So I am like so excited by this. Whoever said it was the find, that is 100% correct. So find, what does it do if it doesn't find something? It returns standard end, and that's just a point to the end of the find array. So that points to out of bounds memory. So this would basically get this out of bounds memory and then access it, and this would cause memory corruption. So this is one of those interesting bugs, and it's one of those things that I, you know, when I saw it, I was like, what? And I think I never would have found it without fuzzing. So I also want to look at the 2 other messengers that don't use WebRTC, and the biggest ones are Facetime and WhatsApp. So I created similar setups that fuzz and replay RTP on each app, and this was more difficult than WebRTC. It required binary modifications because I didn't have the source. So I basically spent months setting this up, modifying the binary. But I did eventually get this to work. So in Facetime, I found 4 vulnerabilities, and one of these was especially interesting because it was a kernel heap corruption bug. So basically, if someone picked up this Facetime call, this would basically could be a straight to kernel exploit with one bug. So that was pretty interesting. And then I also found a heap corruption vulnerability in WhatsApp. But But at this point, I was finished my research, but I wasn't quite sure what to make of it. I had these bugs where, if someone picks up a call, maybe you could exploit them, but I hadn't actually exploited them. And I also wondered, how useful is this to an attacker? How likely is someone to actually pick up a call from a stranger and allow it to exploit and that sort of thing? So I wasn't sure. But then a few things happened. To start off, there was this WhatsApp 0 day. And this was actually pretty shocking. So WhatsApp detected a 0 day that was targeted against dissidents and academics and others. And it was a zero-click exploit. So basically, these victims did not have to pick up their phone. They did not have to touch their phone for their device to be compromised. And it turned out that this worked through video conferencing. That basically the attacker had found a memory corruption vulnerability in the peer-to-peer protocols used by WhatsApp, but they were able to use another bug to make it so that the protocol would be processed before the user picked up the call. So this completely changed how I thought about the video conferencing bugs. Now it wasn't just like, oh, someone has to pick up the call. Maybe there is a way to get this stuff processed before the user picks up the call and make it a purely remote exploit. But then also, maybe this happens already. Maybe you don't need another bug. I hadn't really looked into what Webrtc does before it picks up the call. And, is there the possibility of peer-to-peer exploits there? And then this other thing happened. And this was the group Facetime exploit. And you might remember this. It was a very unusual bug that I'd never seen the likes of before. And what happened is that if you started a group call on FaceTime, and then you added someone who was in the call again, it would pick up the call on their end, even though they didn't touch their phone. So basically, you could force the phone at the other end to turn its microphone on, and you could hear what was happening in the surroundings without the user touching the phone. And this is quite a bad bug. It ended up being a serious downtime incident for group FaceTime because it was something that you didn't need special skills for and was reported for several people, including some middle schoolers. Many people used it, and they had to take group FaceTime down so it would be fixed. And this made me think more. Are there possibly video conferencing bugs where the bug isn't that you can exploit it and steal everyone's messages, but maybe, it's enough just to turn the microphone on so that you can hear a person surrounding? But also, if you can turn the microphone on, then what other protocols are being processed? And is this another way to make these RTP exploits more useful? So I decided it was time to spend some more time on this. So I got more serious about Webrtc fuzzing. I fuzzed for more bugs. I reported them. I found bugs for missing coverage in OSS fuzz, which is basically integrated fuzzing. So I made sure that the fuzzing that is a part of the development life cycle in Chrome and Webrtc was adequately covering all the parts of Webrtc so that, as new bugs got added in, they got found. I also wrote an exploit to determine the exploitability of Webrtc in different applications. So I started off, I found some more RTP bugs. And part of my problem here is, in the beginning, I found a lot of really good bugs. But as I fuzzed more and more, you kind of start to hit the bottom of the bug barrel sometimes. So these were not, the best bugs. And also, Android uses what's called a slab allocator, which means that they don't have inline heap metadata, and that made exploitation more difficult. I did manage to move the instruction pointer using an RTP bug, but I couldn't break ASLR, which is basically, on Android and most systems, they'll randomly load libraries in memory as a security measure so that it's harder to find where stuff is. And that was my problem with this. So I was able to set the instruction pointer to wherever I wanted, but I wasn't basically able to figure out where anything was so I could figure out where to point it. So I had to move on from this. And I started looking at Sctp, which is the other protocol in Webrtc. This is the reliable one that's used typically for peer-to-peer text messages. And historically, I'd found a few out-of-bounds reads, but not a good number. But I decided to give it another look. And I found two vulnerabilities in it. So this one was actually a shocking bug. And I suppose it's actually a bug in WebRTC. It was actually an Sctp integration issue. And the problem here is that the user Sctp software allows what's called custom transports. So, you don't have to use UDP or TCP. You can use whatever protocol you want. And WebRTC used this feature, and they used it to set up DTLS so that it would be a secure transport, which is a good idea. But the problem here is that you have to tell user SCTP what an address looks like. Is it an IP address? Is it some other type of address? And you have to provide this as a void pointer. And what WebRTC did is they provided the address of a specific structure in memory as the quote network address, which basically meant that this pointer was in every single SCTP packet that got sent, which was pretty crazy. That was a memory leak. But what was more interesting was that they would also extract this pointer sometimes from an echoed packet and make calls on it. So this was also like a perfect bug that would allow you to set the instruction pointer. Yeah, it was quite a good bug, and it allowed me to both move the instruction pointer and also somewhat break ASLR. Yeah. So here's the bug if you're curious. This is basically a bad cast. They would take this thing right out of the network and cast it. And what they should have done, and they're doing now, is they use a map. So now they have an integer that represents the pointer in the packet, and then they map it back to the right pointer. So was this enough to break ASLR on Android? It turned out to be no. Knowing one pointer on the heap won't tell you where anything other than the heap is, which was too bad. But I kept looking for more bugs. So I looked more, and I found this use after free bug in SCTP. And what's interesting about it is it had actually already been reported by another Googler, Mark Woodrick, but it wasn't actually fixed in WebRTC because there were some communication problems between the projects. So it was still there. And this bug is more of a subtle bug. Basically, there's this error handling. So if you send a really small packet, it's supposed to not send anything back. So it frees the potential ACK it's going to send. And what it should have done is it returns and then handles the error. But instead, it would just free it and keep moving on. And this would lead to basically it's sending back this ACK packet that could be replaced with something else. And this would usually send back a good hunk of memory in the packet. And what I like about this bug is the green is obviously the fix to it. And this shows like how difficult and subtle it can be to rid your software of these sorts of bugs sometimes. I mean, who among us has not made a mistake like this before, missing one return? Yeah, and unfortunately, this one mistake basically made it so that 1 billion devices now had a remote bug on them so that an attacker could compromise them without touching them. So quite a small mistake for such a serious bug. So I exploited this bug, and I made an exploit that worked on basically a generic Android application, and then I looked for what applications there are on Google Play that had this software in it. And there were 200 apps with more than 10 million installs that had WebRTC in them. That said, most of them didn't have it as a practical attack surface. Part of what was fun about this was that I got to see every use of WebRTC, and there was a lot of them. So one of them was browsers. I didn't look at browsers just because, well, WebRTC bugs do affect them. They're not any more serious than any other bug. They're not any more serious than, say, a JavaScript bug. Also, WebRTC is used for streaming a lot, but that's not a good attack surface because typically when you stream, you upload, for example, an MP4 file, and then the server streams it to the other user. So usually a user doesn't have control over what packets get sent to appear. There was also a lot of, I thought this was kind of cool, projections. So what apps will do is they'll use WebRTC in the app, and then you can link it to the browser, and that'll allow you to use like accessibility features or basically blow up the screen so you can see it larger. But that's not an attack surface, really, because you own both the thing you're projecting to and your phone. So there's no reason that one would try to compromise the other usually. And finally, there was a lot of chat roulette. And well, that is a viable attack surface. All these apps had the problem that there was no reasonable way for me to connect to a predictable user. So I didn't look at them. So after removing these, there were 14 large apps that use WebRTC. And you can see these are all basically big messengers, Facebook, Duo, Hangouts, Viber, Slack, Signal, all of these. And I evaluated all of these for the exploit. I made minor modifications so they would work on each application. And the exploit was fully remote on some and one click on others. So these were the ones it actually worked on. And you might wonder, what about the others? Because this was a bug that used Sctp, it would only work against applications that used Sctp. So a lot of these applications, they would never open a data channel. And some of them even had data channels hard disabled in WebRTC. So that meant that this specific exploit wouldn't work on them. And to be fair, some of these apps that it did work on also tried to disable data channels, but they did it poorly. But this is just one good example of the fact that reducing attack surface does reduce your vulnerability to exploits. Every feature that you're not using, if you turn it off well, it means you're less likely to be prone to a security bug in it. So out of the 14, only 6 of them actually used this feature in a way that allowed me to use the bug in it. What was also interesting was that the impact of the bug was different on different applications. So 4 of them, Duo, GeoChat, Signal, and Mocha, were fully remote. So if I use this exploit, I didn't have to pick up the call at the other side. It would just compromise the device. But then 2 of them were one click. So these ones, you had to pick up the phone for the exploit to actually work. And they also required contacts. So basically, you could only phone a person who you were in their contact list in the first place. So this made it much less useful for an attacker. The difference between being able to compromise any device without touching it, as opposed to having to have the person pick up the call and be in their contacts, is a very different level of effort. So I'm going to show you some videos just to kind of give you an idea of how different this is. So this is Google Duo, and I'm exploiting the device on the right, and you'll notice I don't touch the device at all. So basically, this is just an incoming call, and you can see in my console, the exploit is working. And this device could be in someone's purse or something. It's just getting 2 incoming calls, and then as the phone rings, the exploit is working. And there we go. There's a calc. No user interaction. So that would be very valuable to an attacker. To give a comparison, this is a one-click exploit. So this one, you'll see I do have to touch the phone. So I'm making the incoming call, and then you can see my finger comes in, and I actually have to accept that call. And then look at how long I have to stay connected for this exploit to actually work. So there we go. That was like 30 seconds. So while I'm sure there's situations where an attacker might do this, it's like a very different deal. So what I figured out is that the state machine design is very important. It can be the difference between any problem in WebRTC being extremely bad to being, maybe a useful bug. And I wrote a lot of developer recommendations. If anyone's interested, I can send them links to other talks I've done specifically on how developers can handle this. But basically, it will determine whether you have fully remote or one-click bugs in your application. So I decided I wanted to look more at this. One thing that happened during this research, which surprised me a lot, is I accidentally found 2 bugs that caused calls to be completed without user interaction. So basically, on some of these messaging applications, I wanted to just turn on data channels. And sometimes when I found ways to do this, the call just connected and I could basically hear the sound on the other end, even though that wasn't like even what I was trying to do. And this, especially after the group Facetime bug, made me think, do similar bugs exist? And I spent a lot of time looking into that. So stepping back a bit, video conferencing applications make implicit promises about when audio and video will be transmitted. Basically, it should only be transmitted with consent. So the person should have to answer the call to transmit audio and video. Also, they should only transmit it to the parties that are allowed. There's also other things. For example, you want to assume that, say, your mute button actually mutes your conversation. It doesn't just prevent the other side from playing the packets. You should actually start sending them, stuff like that. So I started to look for audio-video vulnerabilities that basically violated these rules. And there were a few different classes I found. So I was surprised. I found, I think, 6 vulnerabilities like this total. I remember when the group Facetime bug came out, I was pretty surprised. But when I started looking into this, I found that basically every application I look at has this problem. And there's different ways that happens. Signal Messenger and Facebook had similar vulnerabilities, and their root cause is state confusion. So for Signal, it was state confusion between caller and callee, and for Facebook Messenger, it was actually a lack of check whether a call was in progress. But it's the same idea. There were messages that were sent between the device that were intended to be sent in one state, and they were actually sent in another, and this caused the call to be connected. And they both allowed audio to be transmitted without consent. So to explain how this works, this is how Signal would normally start a call. So when you use Webrtc, you exchange what's called an offer, and then you get an answer back. And this includes things like your crypto keys and the protocols you want to use and that sort of thing. And then you can exchange something called Sctp candidates. And this is after the caller and callee have checked out the network configuration based on the offer and answer. They'll come up with like candidate ways to connect. And then they'll connect. Once you've exchanged these, they'll connect, and you'll have this PDP media connection. And this is available, but unless you add what's called a track, that's what enables the camera or the microphone. Nothing will actually get sent. And then what happens in Signal is the callee will press a button. This will add the track on their side, and they'll start transmitting video. And then it will send a message back to the caller so that the caller knows to also turn on video. And the mistake here was that you could send this in the other direction. So you could send offer answer candidate, set up the connection, and send this message from the caller to callee, and this would connect the call, and then you could hear the microphone. And yeah, that was really interesting. And yeah, that was basically a pure logic vulnerability in the state machine of Signal. I also found similar vulnerabilities in Shield Chat and Mocha, and these are the ones that I found accidentally. And this one, the root cause, I think, was that they didn't understand how offers and answers worked, and specifically that they could contain candidates. And these ones allowed both audio and video to be transmitted without consent. What happened here is that this is a server-mediated setup. And actually, all of the setups are server-mediated, but in this case, it actually mattered. Because what they would do is they would send the offer, which would be forwarded on by the server to the callee. Then the callee would send an answer, and then they would exchange candidates. But what the server would do is it would actually save the candidates. And then when the callee accepted, it would send the candidates in both directions. And this is what would set up the call. And then this would trigger an event in Webrtc, and that would enable the track and actually turn on the camera. And the problem with this is that in Webrtc, you can actually put the candidates in the offer or the answer if you have them ready. So that's what I did. I put it in the offer, I put it in the answer, and then this would set up P2P media, which would trigger the event, and this would just cause the call to answer. without any user interaction. Yeah, and this was a situation where I think this was just a pure misunderstanding of how Webrtc worked. And the result of it was that you could easily connect a call without user interaction. And then I found another interesting logic vulnerability in Google Duo. And this one was kind of unique because it was a race condition. And what was fun about it is it allowed a few frames of video to be transmitted without consent. So it could basically turn on the camera very briefly and get a few photos, and then it would turn off again. But that's still, a few more photos than I would like my device to transmit without my consent. So here's how this one worked. The normal setup would be you'd get the Sctp offer, and then it would go through a series of calls. And these dotted lines represent that they're asynchronous calls. They happen in different threads. And basically what this would do is you'd get the offer, and then it would do this set parameters, which would disable video. Then you send back the answer, and then you exchange the candidates, then the media is set up, and then the user would press the button, and then they'd set the parameters back so that audio and video get transmitted. And the problem here is, since these are asynchronous calls, what if this one that disables it is really, really slow? Well, then what happens is this could actually happen after the PDP gets set up. And in that case, it would be, you start transmitting video, and then the thing that turns it off happens. And by then, you've already sent a few frames. And the way I actually did this is I discovered that the Sctp data channel is actually on the same thread as this set parameters. So basically, I would send offers over and over, turn the call on and off, and have a huge data queue that would basically slow down this thread a lot so that these images would get sent. So this was kind of a really fun vulnerability. And the reason it happened, in my opinion, was I guess lack of testing of the state machine, but also needless threading. Did they really need to have two threads here for this one specific call? Not really. They just made everything asynchronous just in case it blocked, and that ended up causing a bug like this. So this led to a number of security improvements. I want to mention, I haven't been talking about them individually, but every bug in this presentation has been fixed. None of them are still available to attackers. Also, Signal and WhatsApp changed their state machines to reduce the attack surface, and other applications are considering this. So basically, Signal did something interesting. They made it so that if someone you know calls you, it works normally. But if someone you don't know calls you, you actually have to press an extra button before it'll even set up the call and do the ringing. And that makes it a lot more difficult for an attacker to use this type of bug against you without social engineering. Now they have to be in your contact list or get you to accept the call like that before they can attack you. Also, user Sctp is in the process of being replaced with more maintainable code. So once again, they're reducing the attack surface, but also making it so that there won't be issues with the gap between bugs being fixed in the main project and getting it into a Webrtc. And as a result of this, several projects have implemented or improved their integrated fuzzing. And this is something I think is really important. I think that if you can have fuzzing as a part of your development life cycle, it really makes it a lot less likely you're going to have serious vulnerabilities in your software. And there's a lot of different ways to do this to make it less likely that these bugs exist. So that's it. One thing I learned from this research is that attacker behavior is an important consideration in targeting research. When I started off, all I had was the table from Zerodium, and based on the prices people were paying for exploits, I tried to do the best guesses I could of what people were doing. And in this research, it turned out to be fairly right, but that's not always the case. Sometimes you just have to look at something with limited information. But then as time went on, I developed more and more information about what attackers were doing, and I was able to target my research more. And I think that's something that's really important to consider. As we do our research, how can we monitor attackers and figure out what's useful to them and focus our time on that? And another thing I think is interesting is, based on what we know now, I think attackers were targeting video conferencing well before my research. And one question I have that I think would be interesting to discuss is, how do we find other areas like this? How do we determine what attackers are looking at now, and how can we make sure that we're also doing research into these areas? And finally, how can attack research be used to thwart attackers? The sort of research we do at WOOT is research on how attacks work, but it's also important to think about, with this knowledge, how do we use this to help the people who are targeted by attacks, and how can we use this to make software more secure? So that's it. I'm hoping everyone can think about these questions as we go through the conference. I know I'm supposed to end with you asking me questions, but I'm unfortunately also ending with me asking you questions. But that's it. And now I have time for questions and discussions. Thanks a lot, everyone.
Awesome. Thanks very much for your talk. This was super inspiring. I have lots and lots of questions, and I see that people are starting to fill out the Q&A. Please use the Q&A tab to ask your questions. And I want to start with not an easy one, but more to get a bit more insight into your process. Assuming you have a fuzzer and you let your fuzzer run, you find 200 crashes. How do you go from crashes to vulnerabilities to decide, hey, this is actually a bug I want to invest more time on? Because a lot of time it's not going to be easily exploitable, but how do you get that feeling for which ones to focus on more and which ones to just quickly report and be done with it?
Yeah, that's difficult. So I do feel like I'm obligated to go through every crash, and I make a point of reporting every one of them. And we do have in our internal fuzzing tools, and some external fuzzing tools have this tool like classifiers that will use, for example, the crash from ASAN to say like, oh, this one's a use after free as opposed to this one is null pointer. But I would say other than that, quite often it is just a gut feel or trying to exploit it, because as you saw in the RTP thing, there were bugs that I thought were really good that didn't turn out, and then ones that did turn out to be very good. And I think, you can tell a bit from the crash dump, but sometimes you do just have to dig in and try things to figure out, which ones are the best.
Mm-hmm. Yep, that makes sense. Rocco Calvi asks, can OSS Fuzz now deliver these vulnerabilities in these software versions? Or does it still need more work? Is there automation for these kinds of vulnerabilities, or is it still lots of manual?
Yeah, sorry, can you say the question again?
Sure, it was in the chat. Can OSS Fuzz now discover these vulnerabilities, and I assume these types of vulnerabilities, in these software versions, or does it still need manual work?
No, OSS Fuzz, and we also use Cluster Fuzz for Chrome tools. Between the two, they can discover these bugs now for sure.
Okay, cool. Roland asks, I thought Android ASLR entropy may not be so high. Handling state machines in C and C++ can be buggy for complex state machines probably. Tools are better to transform the code rather than manual. I think that's an answer to your question more than a question.
Yeah. So for ASLR, I will admit I absolutely walked into this project thinking this, and I was wrong. I think ASLR on Android has a bad rap, but in the new versions, they've improved it a lot. So if I'd used an old version of Android, it absolutely would have been a problem, but the newest versions, I spent a lot of time doing things like histograms, and I asked around, and for the newer Androids, the SLR is actually good. Yeah, handling state machines is, yeah.
Anupam Sarkar, yeah, I think that's the question you wanted to answer next. And it's actually the same question that I had as well, or a similar one. Did you consider looking into stateful fuzzing, as I see some design issues you mentioned? Will that find more bugs? Or more precisely, like, how do you connect all these different states and multiple messages, especially when you go through a very complex state machine?
Yeah. Yeah, so a few thoughts here. Actually, I'm just going to go back to Roland's second question here, which is for state machines, it was rare to find. Actually, I did not find a single state machine bug that was specific to the features of the language. They were all higher level design issues. So it wasn't like, someone wrote C that did the wrong thing. It was that someone, if you wrote out the list of the steps in order, they did the wrong thing. And yeah, the way I did this was, so Signal was the easiest because they actually have their state machine documented. But for the other ones, I went through and figured out how their state machines worked. Since on Android, these are Java natives, I wrote a Frida script that would hook the Java natives, and that would print out the order they were called in. And then looking at the delving disassembly a bit, I could figure out what was going on generally, and then kind of think about, is this sensible? And sometimes it wasn't. I've thought about stateful fuzzing. What I would say is what's challenging about these is I would say some of these systems aren't that reliable, and it's also kind of difficult to detect a situation where you get what you want. So I think this would be something, if I had the source and I was able to kind of extract the state machine and have it not connected to all the other things, I think this would be reasonable. I think the practical aspects of doing this on an Android application where you don't have the source are overwhelming, and I haven't been able to think of a good way to do it. Though I think, if that existed, I think it would be promising.
So maybe, would it be fair to say, instead of doing or creating a fuzzer that does stateful fuzzing, you focused more on individual fuzzing stubs that set up the necessary preconditions so you could then focus on this particular aspect? And then you just tried multiple ones, or?
Yeah, no. So I basically used the stubs just to document the state machine. So I went through, I drew a diagram, and then I just looked at the diagram and thought well, what if I do this? What if I do that? So what I would say, most of the problems were obvious enough if you just understood what the state machine did.
Okay, fair enough. Yeah, I think that makes a lot of sense. Virgilito has a question we get a lot. Will switching to memory-safe languages like Rust prevent these kind of vulnerabilities, making apps that you see seem to be calling for more very basic errors that can lead to bad capabilities?
Yeah, and my answer to this is yes, in my dreams. I've looked into this a bit, and talked to people who do this a bit, and I think that the reality is everyone would love to have WebRTC and Rust. The practical aspects of making it happen are difficult, but yeah, I do think that this would be good. Although this is possibly some of the most performance-intensive code on the web, so performance is a big issue here, which is currently why it's done in C. But yeah. Who knows what will happen in the future. Hopefully it will be WebRTC in Rust, so we don't have these problems anymore.
Yep, that would be cool. How much work is building the testing harness? Asks Will Pierce. And how important are good harnesses? I think it's an important point.
Yeah, so test harnesses are insane for the statefulness, because they weren't full harnesses, it was fast. But for FaceTime and for WhatsApp, this was months and months of work. So yeah, it was very time intensive, and it's very, very important. I think that, especially if you have this sort of software internally, I think it's very important that every vendor has the ability to have a harness that will replay packets that they can use for testing. And I'm surprised by the number of vendors who don't. So it's a lot of time. It's a lot less time if you have the source, but I think it's extremely valuable for security, and everyone who produces this type of software should have one.
Yeah, I think, yeah, that makes sense. Cool. I had one more question. You mentioned in one of the slides that, hey, I just scanned all Android apps. I wish we were mortals had such capabilities as well. But and you checked for usage of certain API and libraries.
Yeah.
In a recent project, we looked at Android apps over time and measured like what kind of native libraries do they include. And as it turns out, this is a really, really hard problem because the native library is not named OpenSSL-1.0.1.f, but like main library.so or something like that. So you need to infer what the library name is first, and oftentimes people modify the libraries. Do you have some internal tools there, or how do you infer these library versions and dependencies and so on?
Yeah, so this was a very frustrating thing. So what we have is an internal tool that can basically grep every library in every Android application. So the way I did this is I searched for basically a string in the user Sctp library, and I considered that good enough. But this was actually a problem that I spent some time on, because before I did this project, there was actually no way to determine the version of a Webrtc library. And now we've at least changed Webrtc so that going forward, there'll be a token. So there should be like a specific thing you can grep for with the version afterwards to figure out if you have Webrtc and what version it is. But yeah, unfortunately, we didn't have that at the time. So yeah, the scanning was somewhat incomplete based on a collection of strings that I thought was like a good representation.
Strings or byte sequences or instruction sequences?
Yeah, they're actually like strings, like log entries.
Okay. Yeah. We ended up doing like a matching on strings as well, but also just exported symbols and a couple of other very simple features that we could use for clustering. And it turns out like people are really, really slow at updating libraries. It often takes 2+ years for people to update and modify these native libraries. Now that you knew that there was a native library, how did you decide what kind of functionality was used? Because you have to cross this language barrier from C land to the Android art Dalvik land.
Yeah, this was another situation where I got out that Python script that hooked the natives in Webrtc, and then I was able to just like run the app and it would print out in what order they got called.
Cool, that makes a lot of sense. Yep, we tried to do something similar. Cool. Any more questions, folks? Amazing work, by the way. That's super cool. If not, thank you very much for coming.
Thanks so much for having me.
Super cool. Will you stick around for a bit so people can actually ask more questions and you can just type and answer them?
Absolutely.
If you're around, so that would be a good way. We have a short break, and I think Fangfei is chairing the next session.